Well, good morning, everybody. My name is George Carey, and I'm welcoming you to our Friday morning presentation that we have going on. I work at FIA, and I have a couple other colleagues online or on the Zoom presentation with me. Rob Ellis will be kind of overseeing the chat. So as we go through this presentation, I'm going to mute everybody. But if you have a question, there's a chat feature down at the bottom of your screen, typically at the bottom of your screen, where you can type in a question, and Rob will try to answer it, live as we're going through the presentation. But at the end, I will ask anyone who has the questions to unmute themselves and ask, and see if we can, do a little Q&A at the very end. This morning's presentation, as the screen describes, is talking a little bit about ECM pumping, residential and commercial, but some of the applications, a little bit of the reason why ECM, and what have you. Some of the popular applications that we've seen, both residentially speaking and commercially. So without further ado, I know we have a lot of people signed up, and then they can see that they're joining as we move through this. But for everybody that made it on time, we're going to start the presentation right now. So welcome, and thank you for coming. ECM, why? Picture of B&Gs, little residential circulators, both cast iron and stainless steel for perhaps domestic hot water or research applications. They also have a family of commercial circulators that we'll talk a little bit about as we go through this. Both single phase, and they actually introduced, I think they're the only manufacturer right now in the market that offers a 3-phase model of ECM pumping for their light commercial or commercial circulators. So a quick question, why high efficiency? What's the reason? What's wrong with this? And this was a typical residential home for a long time, all throughout the country, but specifically up here in the Northeast, New England, New York, New Jersey, etc. 2, 3, 4 zones, 2, 3, 4 zone pumps, 3-piece, old B&Gs. In this particular case, probably looks like maybe a atmospheric gas boiler. And that's what we did. We did for a long time, and everything worked. Relatively speaking, it worked. Now, was it the most efficient way of doing it? Absolutely not. But for years, it really didn't. That question was never asked. But efficiency and energy usage and energy costs and all of that have moved onto the radar screen over the last few years. Probably even more than that when you think about condensing boilers. It's probably been 10, 15 years even. But the industry's changed. It's looking to heat the water as efficiently as possible. And then the next question became, are we circulating? Are we distributing that heated water that we heated efficiently? Are we circulating it as efficiently as possible? And when you get into the details, clearly not. And that was okay, like I said, for years, but now the focus is on high efficiency. Where does it come from? Well, a lot of the things that happen in the hydronics industry seems to kind of originate from Europe. And a couple of interesting factoids, you probably are aware of this already, but residentially speaking, over in Europe, how they heat their homes is about 98% hydronically. So they'll have a boiler of some source, and even those boilers are starting to move to an air-to-water heat pump, but they're using hydronics. They totally believe in using hydronics, using water as the method of delivering energy from the heat source out to the terminal units, out where the people are. And so actually, it's almost 15 years now that the pump manufacturers in Europe got together and they said, hey, are we doing as good a job as we could efficiency-wise in terms of, sometimes you might hear the expression wire-to-water efficiency. How much electricity am I using, and how effectively am I using it to circulate, to deliver the water out to the terminal units? And they voluntarily initially, but they knew, it started voluntarily, but they knew legislation was coming from the European Commission that they were going to increase the efficiency standards of these circulators. So they created this thing called an EEI, Energy Efficiency Index. And they rated the various classes, if you will. They created like an alphabet, A through G is what it's showing here. and so they were trying to get into this A or A asterisk or even possibly A double asterisk. But anyways, they started this a while back, so they've been using it for quite a while. If you look at an ECM circulator compared to, say, a water lubricated, a PSC, a permanent split capacitor, stuff that we've been using, wet rotor, for the last 35, maybe 40 years. When you compare the classes or the ratings, ECM is going to fall into somewhere in this A or A asterisk category, where the stuff that we've been using for the, like I said, the last 30, 40 years, they're going to be somewhere down in that D or E range. And just to go back real quick, you get down in that range, what they're referring to is that EEI. How efficiently are we using the electricity to circulate that water? And so they created these requirements, and right to 5 years ago, basically from January of 2015, this technology, this water lubricated permanent split capacitor, became illegal. They can no longer use those circulators in Europe. They have to be an ECM circulator. So that's been going on for a while over there. Certainly those ECM pumps have made their way across to America, to North America, and specifically up here in the Northeast, where hydronics is kind of predominant. It's kind of interesting, back to that stat about Europe and 98%. In the United States, I ask that question a lot when we have these various presentations over the years. We're about 93% air and 7% hydronics across the whole country. It's very little hydronics. It's all, most of it's located up here in New England, New York, New Jersey. A lot of the boiler manufacturers kind of refer to this section of the country as Hydronics Alley, because that's where all the boilers and all the circulators and what have you, they're all shipped in this neck of the woods. So enough about Europe. What about America? What's happening here? Well, a couple of things. For the first time ever, the Department of Energy, the DOE, is looking at creating efficiency standards for commercial, and eventually, although I think it's mainly commercial at the moment, but it'll reach down into the residential market space, pump efficiency standards. They actually created a study, if you will. Energy Efficiency and Renewable Energy Office has the standards for circulator pumps. And I think they started at, I think it's 2 horsepower and higher. All the pump manufacturers in the United States have to now start to qualify or meet a certain efficiency standard. And eventually, I think they're going to do a second look back, and they're going to start getting into the fractional horsepower. But initially, I think it started at 2 horsepower and up. But that's brand new. Prior to that, that's never happened in the United States. I've had the Hydraulic Institute, which was kind of like a third-party check for the various manufacturers that would say, hey, my circulator, my pump can do this, and they'd publish a pump curve, and the Hydraulics Institute would third-party check it to say, yeah, it does meet that condition, and it is at a BEP, a best efficiency point of 82%, 83%, whatever the number was. But there was never something from the government saying, hey, pump manufacturer, you have to make a pump that can meet this standard. And that's now starting to happen. The interesting thing, especially from the residential market space, and it's going to start to transition into the commercial or light commercial space, is the utilities are very interested in this. They see the value in this ECM technology and the reduction in kW consumption. So all through New England here, Mass Save, which covers Massachusetts and Rhode Island, they have an upstream incentive program that takes place right at the wholesaler's counter, where if you make the decision to purchase an ECM circulator versus a more traditional wet rotor, they're going to take $100 right off the top, off the price of that circulator. So the utilities are recognizing, hey, this high efficiency circulator comes with some technology, comes with some expense. We're going to incentivize, we're going to rebate that so that we can get that technology out into the market space. New Hampshire, they've jumped on board. They have a New Hampshire SAVE program. Connecticut has Energized Connecticut. They have an efficiency circulator rebate program. Vermont, Efficiency Vermont, which was the first guys to get involved, they have a program they offer to all the various manufacturers, different incentives. So you say, okay, well, why? What's so different about these pumps? What's different about an ECM pump versus a more traditional induction motor pump? So from the motor end, which, that's where we kind of got to start with ECM. On a traditional induction motor, which we've been using for the last, probably 70, 80, maybe 90 years, electric current flowing in the rotor is induced by the alternating current flowing in the stator. And the speed of that rotor must be less than the speed of the rotating magnetic field in the stator for induction to occur, hence the name induction motor. And this ratio of the two speeds is called slip. When you move to ECM, what ECM stands for is Electronically Commutated Magnetic Motor. So obviously much easier to just say ECM. But what's happening is on the rotor, they actually have magnets that are attached to the rotor, permanent magnets on the rotor. And that's very different from what we've been doing with the induction motors. Stator coils, which they're kind of showing here, these stator coils generate a rotating field, and the magnet just reacts to this with this magnetic field, and it causes rotation, and for the rotor to turn, to rotate. And what's attached to the rotor but the impeller? So now I control the rotation of that rotor, which means I control the rotation of that impeller, which means I impact the GPM and the pressure differential that this particular circulator can develop or generate. Here's a big difference right here. Motor is microprocessor controlled. There is intelligence on board these circulators. That's brand new. We never had intelligence on. If you get into some of the commercial pumps, you can get into what they refer to as variable frequency drives, VFDs. And now you're starting to add externally some intelligence to the operation of, say, maybe a 5, 10, 25 horsepower base mounted pump, 50 horsepower pump. But on a smaller residential and light commercial pumps, we almost never, just spent the money to have a VFD. It just didn't make sense. But this technology now incorporates that microprocessor. So at the end of the day, power is pulsed on and off electronically to create that magnetic field in the stator. And this process is known as commutation. So electronically commutated magnetic motor. I always go to this slide here because the picture speaks 1,000 words. The color green will represent the north pole of the magnet, and the color red represents the south pole of the magnet. And then what's happening is the microprocessor is pulsing power on and off, and the magnet on the rotor just reacts to that. So the faster the microprocessor pulses that electricity, that power on and off, the faster the impeller and rotor spin, and then the slower it pulses, the slower it spins. It reduces its RPM, its flow rate. And more importantly, and what's got the utilities' attention is as you're controlling, as you're doing speed control, you're reducing the kW consumption. And so that's what, over in Europe, what they were chasing after, what the utilities see the value in bringing this technology over here to the Northeast. And that's why they've, heavily invested in creating these incentives. So lower current requirement, no slip results in greater efficiencies, depending upon, different studies and what have you, 50 to 70% more efficient perhaps than a permanent split, a PSC induction. When the pump turns on, there's a kind of a gradual ramp up to set speed, so it provides a smoother startup. So from the wet end, not a big difference, meaning the wet end of the pump, we have a volute. We have a volute here. We've talked about this over different classes that we've been conducting over the past, X number of weeks. But I have water moving into the eye of the impeller. the impeller's rotating, and the water flows along the vanes and gets flung out the discharge portion or opening of that wet end of the pump, or the volute. Same thing holds true with this ECM circulator. Of course, the difference is I'm going to have magnets on board that router, which is different. And then I'm going to have intelligence. I'm going to have a microprocessor, a PCB, a printed circuit board. Every one of these ECMs has some type of intelligence on board that can influence the operation of how the circulator works. So looking at pump curves, if you look at a traditional wet rotor pump, this happens to be just a collection of some of B&G's smaller residential NRFs. And the point of it all is, when you look at a pump curve, on the far left vertical side, what it's referencing is feet of head, the pressure differential that this pump can develop. On the bottom horizontal, you're looking at flow rate, gallons per minute. How many GPM can the circulator move and overcome whatever frictional resistance a particular system that you're attaching it to offers. But it's pretty straightforward. It's kind of a straight line. You're going to go from your feet of head, maximum feet of head at shutoff, which means shutoff means no flow. And then you're going to run horizontal, or down, I guess you'd say, down to where it intersects the pump curve, the GPM curve, or GPM rating, I should say. And at this point here, it's saying, okay, maximum flow is about 22 gallons a minute at zero resistance, at no frictional resistance. And obviously, somewhere along this line here is where this pump is going to operate in a particular system. Pretty straightforward stuff. We've talked about this already. When you get into the ECMs, with that intelligence on board, that printed circuit board, you can have different modes, and you can actually select a different mode for a very specific application. And with that comes different curves. So if you look at this pump curve, this is referred to as a proportional pressure. We'll spend a little bit of time on this in a couple of minutes, but very, very different than that. Much different looking curve than a more traditional induction or permanent split capacitor pump. And we'll get into that. We'll talk a little bit about that. Another mode that they offer is called constant pressure. And so at any flow rate, they're offering a somewhat of a constant pressure. To be quite honest with you, I don't know how many applications this actually applies to, but it's a mode that they offer within that onboard printed circuit board. Constant speed. We'll spend a little bit of time on this. This is a very popular application that we're using over here in New England and in the Northeast. So the two real popular ones are going to be this: proportional pressure and constant speed. And we'll get into why. So on constant speed, what they're referring to is ideally suited for zone pumping. A lot of times over here, especially in New England and in the Northeast, we might have a residential home that has 2, 3, 4, 5 zones, whatever the number is, and we're going to have the corresponding 2, 3, 4, 5 circulators that are going to be responsible for providing heat for those specific zones. So the beauty of this ECM in this application is I can actually dial in what I need for flow and head, and in doing so, reduce the consumption of electricity. We'll go through a couple of examples as we go through this presentation this morning. Someone had gone out and gone to a wholesaler and purchased X number of ECM pumps, received that rebate, that upstream incentive, and replaced the existing permanent split capacitor pumps with these ECM circulators. And they're just zone pumping. They're just going very specifically, no zone valves, no control valves, just a thermostat through a relay box, pulls a pump on. I can dial in, and now I have speed control over this circulator, which I never had before. This proportional pressure, this is an application where maybe I have one distribution pump, and then my zoning is through zone valves, and they could be electric zone valves or they could be non-electric, either one. Over in Europe, this is a very common application, not so much with electric, but definitely with non-electric valves scattered throughout the home, controlling the output of typically panel radiators, and then they'll have one distribution pump. And the point of this proportional pressure is as these zone valves open and close, it changes the requirements of the system, and the pump has the intelligence on board to recognize that change and either speed up or, more importantly, sometimes slow down as the valves start to close, and in doing so, consume less energy. So ideally suited as a primary pump when zoning with zone valves. So you take that residential pump and you can either do constant speed, constant pressure, or in this application here, proportional pressure. So it's a wordy slide and I don't want to spend a lot of time with it other than this. The onboard PCB, the onboard printed circuit board on each circulator has stored within its memory the operating curve. So it knows where it's supposed to be. So what we're trying to show here is I have an example of, I have a 4-zone home. And here's the mechanical over here, 1 pump, 4 zone valves, feed maybe baseboard. And in this particular case, the contractor said, hey, I'm looking at full flow. I'm probably looking at somewhere around 9 gallons a minute when all 4 zones are calling. And the point of this is, as the zones start to close, instead of backing up on the curve, which is what I would traditionally do with the circulators we've been using for the last, 50, 60, 70 years, and in doing so, continue to consume more energy than needed. And at some point, as I back up and I can develop some excess pressure differential, some excess head, I could actually create some velocity noises sometimes. And that's where pressure differential valves came into play, was to try to eliminate that problem. Well, this ECM with this printed circuit board, with this intelligence, takes care of it. So what happens is, as the zones close and the system conditions change, the pump recognizes that and it starts to slow down. And in doing so, it starts to back down on its particular curve. So as the zones close down, the pump recognizes that, and in doing so, slows down the flow and head developed by that pump. And from the utility standpoint and the consumer standpoint, at the same time, consume less kW. So real quick, this is kind of a look under the hood, if you will. This is a behind the scenes of what's going on. And you never have to spend any time with the consumer talking about this, but what happens is, in the proportional pressure control mode, the motor starts with low speed. The flow and pressure are calculated. How? So the printed circuit board is looking at, okay, how many watts am I consuming and what's my RPM? And based on that, it knows where it's at. And then it says, okay, reference the calculated, reference pressure is calculated based on the potentiometer. So that's the dial on the circulator. Where did you set it? So real quickly, you set it on this example here. Some contractor perhaps set it on dial 3. Said, hey, I'm looking for this kind of flow rate on design conditions when all 4 zones are open. So the control says, okay, I'm on dial 3. So I know the curve. I know in my memory, I know exactly where I need to be, and it's based on wattage and RPM speed. And so the control says, okay, I'm running. This is what I'm set for. Is there a difference? Is there an error? And if there is, the pump speed should be either increased or decreased, automatically accordingly. And it's almost instantaneous. You really can't see it happening. It happens so fast. It's a computer on board telling the pump where to be. So this is the potentiometer. This is the dial that I was referring to. It sits right here, and you make that adjustment, respective to the particular zone you're putting that, or the zone, the application they're putting that circulator in. And once he's set to a particular dial, and you told him, hey, you're going to be running in proportional pressure, he knows where he's supposed to be all the time. So as conditions change and the pump starts to either speed up or slow down, he says, I'm not on my curve that I'm supposed to be on, and I'll respond accordingly. So I want to spend just a couple minutes here, just real quickly, how this can be applied and why the utilities, how this got the utilities' attention. How to apply flow and head information to existing systems. So we have a lot of installed hydronic systems up here in New England and in the Northeast. And a lot of times we do zone pumping. So I just want to take you through a couple quick examples of how you could take advantage of this technology, this ECM with this dial right here. And then I think some of you guys might be familiar with this wheel, this calculator, the system sizer. We did a class a couple weeks ago. We got another class coming up, I think in a week or so, on the system sizer. So I want to combine the capabilities of this tool and how you can use it to take advantage of the efficiency that comes with this circulator. So, quick example. I have multiple zones in a home, but I'm just highlighting one particular zone for example. And in that particular zone, I've got 30 feet of 3/4 inch copper baseboard. Now, I'm not sitting here doing a heat loss calculation, which is what I really should be doing, but I'm going to say, look, at the worst case scenario is I've got 30 feet of 3/4 inch. How many BTUs does this represent for that particular zone? And what you do is you could go to any baseboard manufacturer's literature and say, okay, standard water temperature, typically 180 degrees. Maybe I'm only, whatever my flow rate is, but say 580 BTUs per linear foot of board. And I have an application where I have 30 feet of it. So I'm just going to do a math equation. 30 feet times 580 represents 17,400 BTUs an hour. So in that one particular zone, that's the maximum BTUs I'm going to transfer into that space. So then the question becomes, okay, as a circulator, what does that mean in flow rate? How many gallons a minute is that? And that's where I could take advantage of that system sizer, the calculator, and say, okay, I have a load of 17,400 BTUs. Almost all, I won't say every, but almost all residential systems are going to be designed on this 20 degree right here, delta T. And that's what that symbol is right here, delta T, temperature difference. So when I line up that 17,400, all I have to do is look down here in the small window and it says GPM. Sorry, it's cut off right there, but that's represented GPM. So all I'm saying is 1 gallon a minute, 1.5, 2 gallons a minute. So I'm really, technically, I'm pumping like 1.7, 1.8 gallons a minute to transfer 17,400 BTUs. So then the next part of the equation is, okay, and now I know my flow rate when I pick a circulator, what's the pressure drop? What's my frictional resistance in that zone that I need to overcome to provide that flow rate? So in this example here, what's the pressure drop of 100 feet of 3/4 inch pipe with a flow rate of 1.74 gallons a minute circulating through it? Again, system sizer, now I move to scale 2, and scale 2 is all about pressure drop and pipe size. So I say, okay, it's an existing system. I know I have 3/4 inch copper pipe that I'm flowing through, and I know my load is 1.7, 1.8 gallons a minute. What's the pressure drop? So here's my 1.5 gallons a minute. Here's my 2.0 gallons a minute. So I'm right around here, 1.8 gallons a minute. And the pressure drop is a little over 1 foot for every 100 feet of pipe. So then you say, okay, well, what's the total pressure drop? Well, what you have to account for when you get involved with figuring out the total length of a circuit is you got to include fittings. And a rule of thumb that we've used in the industry forever is instead of sitting there trying to figure out how many fittings are installed in the system, is just take the 50% rule. Whatever the length of run of that zone is, add 50%, and that will account for your T's, your elbows, etc. So if I say, my total pressure drop, my total TEL is 150 feet, and I'm lined up opposite my pressure drop of about 1 foot. At 150 feet, my total pressure drop for that circuit is about 1.5 feet of head. So then you say, okay, what does this all mean? Let's go back to the pump curve and say, okay, here's my Eco 1916 curve. I have a flow rate of 1.74 gallons a minute I'm looking for. And in that circuit, that 100-foot loop, add the fittings, it becomes a TEL of 150. I have a pressure drop of 1.5 feet. So when I look at that potentiometer, I have a dial that I can set. It's right over here on the right-hand side of the circulator. I can make an adjustment. I can dial that pump to right into that particular zone. So in this example here, with 1.74 gallons a minute, overcoming 1.5 feet ahead, I can put it down to dial 1. You say, okay, well, what's the benefit of that? How many watts am I consuming at that setting of 1 on the potentiometer? I'm consuming about 5 watts for that one zone. So anytime that thermostat in that particular zone of 30 feet of baseboard calls, I'm going to be using 5 watts to circulate the desired flow rate. So then you start saying, okay, well, what does it cost to run a zone pump? And that's where the utilities come in with this incentive. Typically, little residential water lubricated PSC, permanent split capacitor. Our version would be like an NRF22 or so. Typically, they consume around 85 to 90 watts anytime they turn on. So then you start plugging in some numbers. Average heating season here in the Boston area, which is where I kind of based everything on, is about 4,600 hours. And the average heating season, 4,600, assume a zone pump is running around 2,300 hours, half of that. So then you say, okay, 2,300 hours times 90 watts, I'm consuming 207,000 watts. I want to figure out my kW consumption, so divided by 1,000. So I'm using 207 kW per hour. When I did this example, the cost per kilowatt was about 20 cents. I probably should update this because I'm sure it's a little more than that. But anyways, at the end of the day, when you do the math, to turn that circulator on, a traditional pump, which we've been doing for the last 40, 50 years, that pump's going to consume about $41.40. Now all of a sudden I replace it. I go to the wholesaler and I pick up a couple of replacement pumps. I take advantage of the rebate at the counter, and I'm going to put in an Eco 1916, consuming 5 watts, plug in the same numbers, do the math. I'm only consuming 11 kW per hour. So to run that pump for 2,300 hours out of the heating season, I'm consuming $2.30 as opposed to $41.40 on that one particular example. And that's what's caught the utility's attention. That's what's driving it. They're very interested in this. Just one quick, I'm just going to fly through this real quick, but someone says, you know what, 30 feet's really not, that's kind of a small zone, make it bigger. So we said, okay, let's make it 50 feet. Times it by the 180, I got almost 3 gallons a minute, 2.9 gallons a minute, 30,000 BTUs. And the loop is 200 feet, not 100 feet. Do the math, use my system sizer, do my calculation, overcoming about 8 feet of resistance at a flow rate of 3 gallons a minute through 3/4 inch pipe. So I apply it to the curve, the pump curve, and I say, okay, I'm trying to pump 3 gallons, 2.9 gallons a minute, and I need to overcome about 8 feet, 8.3 feet of resistance. So in this case here, obviously dial 1, the potentiometer setting, that'd be way too low. It doesn't have the flow to overcome the resistance. But I find that I can set it at dial 4. So you say, okay, well, what's the energy, what's the wattage consumption? Well, it's about 20. Well, 20 is significantly more than 5, but substantially less than the maximum here is 60. And what you were taking out is around, like I said, 85, 90 watts. So it's still a savings. You do the math, crunch the numbers. That particular zone with the 200 feet plus your fitting, so call it 300 feet, 8 feet of resistance, 3 gallons a minute, it's going to cost you about $9 a year, $9.20. If it's running for 2,300 hours, and the cost is 20 kW. It might be a little bit more now. But anyways, the point of it all is it's substantially, you can take advantage of this constant speed, that potentiometer, and you could really fit or set the circulator for the specific zone that it's being installed in, which we've never done. We've never done that in the past because we had no speed control on these residential circulators. Kind of moving forward, same concept, it's just carrying forward to the commercial version of the Eco XLs is what Bell & Gossett refers to. And again, like I mentioned at the beginning, they come in single-phase models and they also offer 3-phase models and more capacity, obviously. One interesting note, in their model number, it's kind of the first time that Bell & Gossett's had a model number that kind of represents the capacity of the pump. And what I mean by that is this. When I look at this Eco XL, and then it's 36-45, what it's referring to is at no flow, the maximum head that this pump can develop is about 36 feet ahead. And then on the 45, what that's referring to is the max flow. So with no pressure drop, I can move 45 gallons a minute. So in my mind, I can actually start to see the shape of that curve, 36, no flow, 45, max flow, no head. So I can start to see it. It's the first time B&G's had model numbers like this that kind of represent or reflect the pump curve of the particular pump. So we kind of categorize these circulators or these ECM Eco XLs in 2 categories. One's referred to as a high head model, And, it's moving GPM, flow rate, but it's overcoming, feet of head, frictional resistance. And these are what you refer to as some of the higher headed model numbers. And they're showing them both in the three-phase and the single-phase models. And some of them actually have the option of becoming either three-phase or single-phase. And that would be this 770-145. So you get some decent flow rate over here, with these high-headed pumps. And then the second part of the family is the high flow models. The same thing. New three-phase offerings are in the white. And then they double it up and they say, look, you can pick that pump in either three-phase or single-phase with this 40-275. What I just want to point out here is these flow rates, they're pretty substantial. 250 gallons a minute is 2.5 million BTUs at a 20-degree delta T. 300 gallons a minute is 3 million BTUs. That's pretty substantial. Look, we've got some decent capacity here with these ECM circulators. And what's happening is these drives that are on board, that's the intelligence. Similar to what we talked about in the residential, but just even more capability, as well as some display features that reside on these commercial pumps. And just like the residential, they come constant pressure, proportional pressure, constant speed, or constant curve. They add this other feature, which they refer to as night setback. I don't know how many times it's being taken advantage of, but you could actually operate any one of these three modes and incorporate night setback. It's an option, doesn't have to be used. The constant pressure, like I said earlier in the residential pumps, I don't know how applicable it is, but you could have some applications that are talking about maybe some smaller or constant pressure loss systems where you could use constant pressure. This is a real big one. This is probably our most popular application, like we said earlier in the residential proportional pressure. Put it in an apartment building, multifamily unit where you have, X number of apartments or zones, and they all have their own thermostat, and they all have their own, some type of zone valve, either electric, like we're showing here, or maybe a non-electric. That's a very popular application, and we do this, meaning we, FIA, we see this application quite a bit. I don't need to go through this. We've already done it. What I wanted to show you here is, here's a quick example. Proportional pressure on a 65-130. So I've got maybe I've got an application where I have, let's see here. Maybe I've selected this particular pump, and I'm looking at somewhere around 750,000 BTUs. That's the load. So I'm looking for around 75 gallons a minute. And I have this proportional curve. And the way it's developed, the way the manufacturers of these ECM pumps, when they get into proportional pressure, what they do is they take whatever the design head loss, whatever your frictional resistance is, where they try to land the proportional curve is they'll take H and divide it by 2. So whatever my design head is over here, I'm going to back down on this curve down to basically about half of what I can develop at my design conditions. So it's speed control. You can see the RPMs. We're just slicing through, we're cutting through these RPMs. And it's not a very steep curve, if you will, on the speed control. So you're saying, how much benefit is that? When you apply it to the power consumption, the wattage over here, it's a very steep curve. So I can go from consuming anywhere from around, maybe 800 or so watts at maximum design flow. I can drop that thing all the way down to as low as perhaps 200, 225 watts. So that's where the energy savings is. And that's what this pump will do constantly as the zone valves upstairs continually open and close, responding to a thermostat call. Fixed speed, we've talked about that. This is an application where there's no zone valves. I'm just going to a very specific load, whether it be a fan coil, an air handler. It could be baseboard. It could be, in this example here I'm showing, this was an application that they had a multifamily unit. So they were using 2 pumps, one running, one is 100% standby in proportional mode, feeding zone valves upstairs. And right beside it, they had another set of 2 pumps, and they were going to be in constant speed, and they were feeding a bank of 2 or 3 indirects. and the ability of this pump to kind of dial in the desired flow rate that the manufacturer of the indirect wants per coil, you could actually do that. So you could set it up, it's constant speed. You're saying, okay, buying an ECM pump is a little more expensive perhaps than a more traditional wet rotor, but you have some other capabilities that we're going to get into where you can have these pumps kind of talk to each other and rotate and all of that. So this is a pretty common, we see this a lot in these light commercial applications where we'll do proportional pressure for the radiation upstairs through zone valves, and then our indirect, our domestic hot water, it's a constant speed, but we can actually dial it in so it's not consuming more than it needs to satisfy the design conditions of the coils inside these indirect water heaters. Kind of following up on that, parallel operating modes. We can have the pumps talk to each other. There's a cable that will run from one head to the other. One of these circulators will become the leader or the master, if you will, and the other one becomes a member, and they communicate back and forth. They offer up to 4 modes of operation. I think 2 of them are very applicable, and then 2 of them, I don't think they make that much sense. But the first operation would be backup. Only the lead pump runs. If the lead pump was to fail, the second pump starts. It's an option. I don't think it's very applicable. I think this is more appropriate right here. Alternate operation. Again, you're designing it so that the one pump can handle the load, and it runs, when there's a call, or maybe you use an outdoor temperature and it's running all the time. But what happens is they switch operations every 24 hours. So you get an equal runtime on both circulators. The other benefit would be is if the pump that's supposed to be running, it's his time at that moment, and he fails, the second pump can automatically start and pick up on the failure of the lead pump. Here's another operation, or application, I should say, of parallel pumping, where you could take advantage of some of those larger, maybe those high flow pumps, and put them in parallel. And you can cover a lot of ground. You can get into 4 or 5 million BTUs, 400 or 500 gallons a minute, 600 gallons a minute. So what would happen is the piping would be sized for that total flow, and then you'd pick 2 pumps that could provide half of that flow at the design head loss and run them in parallel. And when they're talking to each other with the intelligence that's on board, what's going to happen is both pumps will run simultaneously at that same set point. And then what happens is as the load changes, the lead pump can either start or stop the second pump to satisfy the required performance. Meaning, if the load gets light enough, the lead pump might say, you know what, I don't need a second pump to run. All I need is the individual pump, so I'll even save more energy and I'll shut that pump off. And then as the load starts to pick up and I can't handle it myself, I'm going to bring my second pump back on and we'll run together simultaneously at the same set point. The fourth option that's available on this parallel mode is what they call forced parallel, and both pumps just run simultaneous set point. We don't take into some of this intelligence of cycling that second pump on and off. So I think the parallel modes are right here. Either having 100% operation and then I'm just going to rotate my lead and my lag, or if I do a little bit of engineering and I pick 2 smaller pumps, when I add them together, I get my desired flow rate and then have a little bit of intelligence on board. This is just a snapshot of an example of pumps out in the field. One of the benefits of these, in addition to the energy consumption that we've been talking about, is they got displays. So you can actually see what's going on this pump. And you can, as you scroll through this button right here, you can see watts. You can see the GPM is highlighted, it's in green. You can see the feet of head that the pump is developing, and you can see the speed, the RPMs. You can see the mode of operation right here, and we're doing proportional pressure. That's the icon, if you will, for proportional pressure. And the reason for that is it's feeding a multifamily home upstairs, a bunch of apartments with their own thermostats and zone valves. And over here, this guy is in standby. So what would happen is if you were show up the next day, you just have this pump running, and this pump now would display standby. So it just rotates back and forth. Another option for these circulators is temperature. temperature control. Behind the impeller on board in the volute, there is a built-in fluid temperature sensor right there. So I could do, what I could do is I could add an external temperature sensor that I could locate perhaps on the return, and I could do a delta T. I could do a temperature difference. I could dial into the pump and say, hey, maintain 20 degrees on this loop, whatever that loop happens to be. And looking at the supply, which is typically where the pump's going to be on the supply with the built-in sensor, and compare it to the temperature on the return, I could influence that pump's speed, its operation, based on the delta T. One other application I just want to point out here that's available with these EcoXLs is they have the ability to receive an input, a 0 to 10 or 4 to 20 milliamp input to influence the speed of that pump. Where we're taking advantage of it is we're combining technologies that are available through LockNVar on their smart control, where they can provide a 0 to 10 output, and then we marry it or match it with an EcoXL that can receive that signal and vary its speed based on the information or the power signal that's being provided by the boiler. And the boiler is looking at what's happening on board on the boiler. So just real quickly, going through an example that would happen when you have fixed speed circulators on your boiler pumps, which up until now has been, that's what we typically would do. So they're showing an example here where production flow with a boiler plant equals the distribution, the system side. So I have perhaps some type of outdoor reset schedule where the controller is saying, hey, I want 140 degrees. And the secondary pump is pumping 150 gallons a minute out to the building. They designed it on, looks like a 40-degree delta T, so I'm coming back at 100 degrees at a flow rate of 150 gallons a minute. I have one boiler running, full flow, 150 gallons a minute. So what's happening right here is there's no flow in the common pipe. That's subject of primary, secondary that we talked about a little while ago. And so, everything's good. But then all of a sudden, maybe the load out here on the building, the distribution side, changes. And all of a sudden the secondary pumps, the VFDs ramp up, and now they're pumping 200 gallons a minute. And I only have that one boiler and boiler pump running, so I'm providing that 150 gallons a minute. With that higher flow rate, what's going to happen is I'm going to have some flow, 50 gallons a minute to be exact, moving up the common pipe. So I'm taking some of that 100-degree water, moving up the common, and now I'm going to blend with the 150 coming out of my boiler to satisfy the 200 GPM that I'm looking for. But in doing so, when blending, I'm knocking down the supply temperature from 140 to 130. And the outdoor reset schedule is going to say, hey, I'm based on my conditions or based on my settings and the current conditions, I need 140. Boiler 2, you better come on. And it does. So now I have fixed flow of 150 on boiler 2, fixed flow on boiler 1. I have a total on my boiler plant, my production, of 300 gallons a minute. The secondary pumps or the distribution pumps are only looking for 200, but they're going to get their 200 at their desired flow rate of temperature of 140. But now I'm over pumping the boiler plant. So 200 out to my secondary, 100 goes down the common pipe, blends with the 200 coming back of 100-degree water, and now I start to elevate my return temperature. And if I'm dealing with condensing technology, ModCon boilers, the last thing you want to do is elevate your return temperature because it can take you out of that condensing range. So with fixed flow, this is a scenario that would happen. And so a solution perhaps could be this variable speed, this ECM technology that can take that 0 to 10. So in this little slide here is just saying, hey, efficiencies. How efficient is the boiler? You buy in a 95%, 96% efficient boiler. If the boiler is seeing 100-degree return water temperature, depending upon its firing rate, whether it's at 4, 50, 100%, it's going to be at a certain efficiency. If you start to take that 100 and start to elevate it, and the reason we're elevating it is we're over pumping that common pipe. We're going backwards. We're taking some hot boiler water and dumping it into the return. I can start to lower the efficiency of that plant. So we try to avoid that when possible. And now that this ECM technology is available and it's out there, and it has that ability to receive this external signal from the boiler control, you can kind of, eliminate that from being a problem. So what I'm just showing here is I have a, again, maybe it's a 500,000 input condensing boiler with a fixed flow. And as the boiler modulates, and why would the boiler modulate? Because the load on the building is constantly changing. In fact, it's very rarely at design conditions. I'm going to vary my firing rate of my boiler. And when I do that with a fixed speed pump, look what happens to my delta T across this heat exchanger. My inlet and my outlet gets very, very tight. That can lead to short cycling of that boiler or boiler plant. If I was to make a change and incorporate an ECM circulator that can take that 0 to 10 so I can vary the speed of the pump, and what's going to dictate the varying of the speed, I'm going to look at my inlet sensor and my outlet sensor. I'm going to calculate, or set, I should say, not calculate, but set a particular delta T. In this case here, maybe it's a 20-degree delta T across the heat exchanger. So what I'll do is, as the control varies the signal, which influences the speed, I will change my GPM as the boiler's firing rate changes to maintain that set delta T. Does a great job of eliminating or minimizing cycling or short cycling of this technology, which is that's a positive. So we had a system out in the field that we just took a couple of screenshots. It happened to be St. Stephen's Community Complex. And what I wanted to point out here is space heating runtime, 1,550 hours. And then space heating cycles was 131. And when you do the math, the boiler was actually running for almost as long as 12 hours per cycle, which is very effective. So what happened there is we had multiple boilers, and each boiler had a variable speed pump, an Ecocirc that could receive a 0 to 10 signal. So you could really fine tune the production of that heat source, that boiler plant, and run it very, very efficiently. So that's the last thing I want to mention about ECM with these larger light commercial pumps. They also come in stainless steel, so from a potable water, possible recirc in apartment buildings, we've entered into that arena as well with these circulators, and they do a nice job. One last comment, and we're coming to the end here. And you guys, a lot of people that are online right now, probably attended one of our Boiler Mag presentations by Mark Ward. But what happens when you mix magnets, and that's what he was referring to, is you have these magnets that are on board these ECM circulators, and then you have iron oxide, within the system. And so that's what that's where Boiler Mag kind of comes into play. We typically want to locate it on the return before it gets to both the appliance, the boiler, and then over here you're going to have your circulator or circulators. You want to catch some of that iron oxide, because if you don't have some type of magnetic separation, the magnets on the ECM start to act like a boiler mag, like a magnetic separator. So here's just a kind of a look of a residential version, inline, showing it, taking it out, what it looks like, being covered with the iron oxide. Some of the larger sizes, as you get into larger diameter pipe, a little bigger. Ideally, we want to go what they refer to as full flow, but sometimes economically, maybe it just can't. It doesn't make sense, so you just can't get there. The price is just too much. So they get into what they refer to as side stream or a bypass. And that's okay. It's just you're not catching everything first pass, but over a period of time, all of that magnetic oxide, iron oxide would pass through that magnetic separator. And that's just showing a picture of a bypass, what a spec might look like. And here, if someone had taken a picture and sent it to us, that's pretty nasty. That's the stuff that would have landed either in the boiler on the heat exchanger, perhaps, or more likely, if you were using ECM technology in that system, it would probably land in the impeller and probably even cause the pump to seize up. So it's kind of like the third leg of a stool. High efficiency boilers, modulating condensing, high efficiency circulators with intelligence on board, ECM pumps. And then the third part is water quality or protecting your investment by using some type of magnetic separator. And with that, I have come to the end of the presentation, and I would open it up to, I don't know if anyone has any questions.